In this module, we're starting to explore some basic right triangle trigonometry. And in the first lesson in the module, we're looking at a certain ratio. So a little bit of vocabulary. We've talked about right triangles before. The hypotenuse, remember, is the side opposite the right angle. So in the triangle on your screen, you see segment AB is the hypotenuse. Notice that it is opposite right angle C. Angle A is the angle that we're talking about, specifically finding certain ratios regarding that angle. And in order to do that, we need to make sure that we know what opposite and adjacent is. So a lot of times students struggle with what side is opposite an angle and what side is adjacent to it. The word adjacent just kind of means next to it. But notice that it's leg adjacent to angle A. So you have to know that AB is a hypotenuse, and so that disqualifies it from being the leg adjacent to angle A. So what's the other side forming angle A? Segment AC. So that's the leg adjacent. Opposite, if you were to draw a line straight through angle A, you would land at the leg that is opposite the angle. So sometimes that helps. So in this Explore, they're having us draw a triangle DEF and label the legs opposite and adjacent to them. So you have something similar to that in your book. And then what they're wanting to do is to calculate the ratio of the opposite leg length to the adjacent leg length. So what I've done, rather than draw a bunch of triangles, is I built this so that we can see many triangles. Notice that the instructions wanted us to draw a right triangle so that angle D was 40 degrees. I couldn't get it to exactly 40 degrees, but that's pretty darn close. And then it's measuring the length of EF, and it's measuring the length of DF, and it's setting up the ratio. So notice that as I click and drag this triangle, the lengths of EF and DF are changing, but notice how the ratio EF over DF, well, that's not flinching at all. That ratio is approximately 0.84. And in part C of this, it's asking us to draw a different triangle so that it's similar to it. But in the geometry sketchpad that I just showed you, I showed you multiple different triangles. And so what was the ratio of the opposite leg over the adjacent leg? It was always 0.84. And so again, if we were doing this in a traditional classroom where all of the students were doing this activity, we would see that, yes, all of the triangles would have the same angles. Again, if you consider here, the angles of these triangles are always the same. Notice that that 39.99, that's not flinching. I constructed it so that this angle F is constantly 90 degrees. So the angles are always the same. Do they always have the same side lengths? Not all triangles have the same side length. But they all have the same ratios. So if I repeated steps A through D with a right triangle having a 30-degree angle, how would my results be similar? Well, it's pretty easy to do that with technology. Let's take a look. Okay, so I'm going to move this point E so that it's a 30-degree angle, and I think that's about as close as I'm going to get. So Notice angle D isn't changing, it's 30 degrees. Notice that the lengths of EF and DF are changing, but that the ratio of EF to DF is staying the same. It's 0.57. Okay, so how would my results be similar? The ratio is constant. That's how they're the same. How the results are similar, rather. How would they be different? The ratio is smaller. So that ratio that we calculated, it's called the tangent ratio. And so the definition of tangent is given to you there. It's the ratio of the length of the leg opposite angle A to the length of the leg adjacent to angle A. And so here we're talking about how all of those triangles were similar. And they're similar by angle. And we also know that every time I made that triangle bigger or smaller, let's say this was the original triangle I started with, when I made it bigger, it was being multiplied by a scale factor of k, and so that's why KL is equal to EF, or I'm sorry, KL over JL is equal to EF over DF. So that ratio is always the same. So in example 1, they're asking us to find the tangent of angle A. So in part A, opposite angle A is 18, adjacent to angle A is 24, and when I put 18 over 24 and reduce it, I get 3/4. They've gone ahead and evaluated that fraction to convert it to a decimal, and they got 0.75. In part B, I'm trying to find the tangent of angle B. So that's the length of the leg opposite angle B over the length of the leg adjacent to angle B. So the leg opposite angle B, if I go from B straight through the middle, where do I land? I land at 24. So 24 over, what's the leg adjacent to 24? Well, 30 is the hypotenuse, so that's not it, so it must be 18. And 24 over 18 reduces to 4 over 3, which is approximately 1.3. If you want to be exact, you can write 1.3 repeating. So what is the relationship between the ratios for tangent A and tangent B? Notice here, they're reciprocals of each other. Oh goodness, I can't spell. Reciprocals of each other. Will this relationship be true for acute angles in other right triangles? Yes. The side, or the leg, excuse me, the leg opposite one acute angle is adjacent to the other acute angle. Why does it not make sense to ask for the value of the tangent of L? Right? Well, what angle L are they referring to? They're talking about this triangle, and in triangle JKL, L is the right angle. Well, the definition of tangent is leg opposite the angle over leg adjacent to the angle. Well, angle L is my right angle. The side that's opposite angle L is the hypotenuse. There is no leg opposite the right angle. That's why it doesn't make sense, because there is no leg opposite the right angle. In this Your Turn 5, we're asked for the tangent of angle Q. So, tangent Q equals leg opposite Q over leg adjacent to Q. And the leg opposite Q is 15. The leg adjacent to Q is 36, and you're in high school, reduce your fractions. This reduces by a factor of 3, so I have 5 over 12. Pause your video to work through the Your Turn on your screen, number 6. In this example now, we're using trigonometry to find an unknown length. So the question is asking, to the nearest tenth of a foot, how far above the ground is the eave of the roof? I'm not terribly fond of the way that they did that. If you look at this triangle, and you see where it translates in the diagram, here's the ladder, and notice that it reaches the eave of the roof. So what they're asking us for is this length. So I know that the tangent of angle A is going to be the length opposite angle A over the leg adjacent to angle A. So they have that labeled as BC over BA. And then identify the given values and substitute into the tangent equation. So they have that BA is 6, so you see that they've substituted 6 in for BA, and then they have the 76 substituted in for angle A. And then we're just kind of solving for our unknown length. So here we see that they're multiplying both sides by 6 in order to get BC by itself. So you're multiplying 6 times the tangent of 76, which is a value you get out of your calculator. There is nothing that you can do in your head or on a 4-function calculator in order to get this value. Okay, so if you have not yet acquired a scientific calculator, you need to get one right away, because you're not going to be allowed to use your phone's calculator on a test or quiz. So make sure that you're getting a scientific calculator. And then they found the value to be 24.1. So the eave of the roof is 24.1 feet above the ground. In part B, I'm asked for the length of the leg adjacent to angle S. So they've got kind of the whole thought process laid out for us, so let's fill in as many blanks as we can. I know that the definition of the tangent of S is that it's going to be the length of the leg opposite angle S over the length of the leg adjacent to angle S. So angle S is opposite TU, and the leg adjacent to S is SU. I'm given that TU is 87. I'm given that angle S is 54. I substitute in the values I know, and now I have that the tangent of 54 is equal to 87 over SU. So this time my variable is in the denominator. So what they have us doing is multiplying both sides by SU and then dividing both sides by the tangent, typo alert, of 54. So when I do that, I'll have that SU equals 87 divided by the tangent of 54. Now, this step I'm not terribly fond of. I see no reason to find the tangent of 54 and substitute it into the equation. I would rather you not do this, but just do all of this in your calculator in one step in order to find the length of SU. So in your calculator, you're going to take 87 divided by the tangent of 54. And when you do that, you find that SU is approximately 63.2. I need a ladder to reach the second-story window, and that second-story window is 10 feet above the ground. So here's a house, here's the window, and it is 10 feet above the ground. I need that ladder to make an angle with the ground of 70 degrees. So here's my triangle. This angle here, that's 70 degrees. How far out from the building does the base of the ladder need to be positioned? That's my X. Okay, so now that we have an idea of what's where in this problem, maybe we want to draw a triangle that is separate from this pretty little picture here. So this is 10, this is X, and this angle is 70 degrees. So I know that the tangent of 70 will equal ten over X. And another way that I'd like you to consider how to solve the equation when X is in the denominator, think of this as a proportion. And how in a proportion, if I have two things across a diagonal from each other in a proportion, well, no matter where they are across that diagonal, they would cross multiply with each other in the process of cross multiplying to solve it. So let's go ahead and switch these things across the diagonal. And when I do, I get X over 1, but I really don't need that over 1, equal to 10 divided by the tangent of 70. And at this point, you're typing that into your calculator in order to find the distance the base of the ladder needs to be positioned away from the house. So 10 divided by the tangent of 70, and that is approximately 3.6 feet. In our previous examples, we were using the angle measure that we knew and a leg measurement that we knew to find an unknown leg. If, however, I know two leg measurements and I want to find the measure of the acute angle in the triangle, then I would be finding the inverse tangent. So if you look at your scientific calculator that hopefully you've been using, if you look above your sine, cosine, and tangent buttons, specifically your tangent button right now, you see above the tangent button a tan -1 function. And so that's what we're using in order to find an angle measure. So in example 3, part A, we're finding the measure of angle A. We know that the tangent of angle A will be the leg opposite angle A, the 19, over the leg adjacent to A, which is the 36. And then in order to find angle A, I'm taking the inverse tangent of that ratio, the 19 over 36. And then I'm just using my calculator to find the angle measure. We're going to do the same thing for part B. So in part B, the tangent of B is the leg opposite B, which is 36, over the leg adjacent to B, which is 19. So in my calculator, I need to evaluate the tangent -1, the inverse tangent of 36 over 19. And when I do that, I get 62 degrees. In this your turn example, we're doing the same thing. We're finding angle J. Okay, so remember that tangent of J equals leg opposite J over leg adjacent to J. Opposite angle J, we have 46. Adjacent to angle J, we have 93. So that means that the measure of angle J equals the inverse tangent of 46 over 93, which is approximately 26 degrees. So how do I identify the opposite and adjacent legs of an acute angle? For opposite, draw a line straight through. For adjacent, it's the leg next to the angle. How does tangent A change as the measure of angle A increases? Well, I've still got that sketch. Let's take a look. As angle A, or in this case angle D, gets bigger and bigger, what's happening to my ratio? It's getting bigger and bigger. And if I wanted to, I could make it go up and up and up and up and up forever and ever, and it would get really, really big. Okay, so tangent of A increases as the measure of angle A increases. Because as angle A increases, the leg opposite angle A, which is the numerator of your fraction, gets bigger.